Hello everyone, this is Kagolo Fridaus from Group 17 and we are presenting our concept paper and our EDA visualization, and our topic project is the multi-strategy psychological signal processing for intensive health care using ECG knowledge distillation. Well, our abstract is that the electrocardiogram signal processing plays a crucial role in cardiovascular health monitoring, enabling early detection and diagnosis of potentially life-threatening conditions. However, the inherent challenges associated with ECG data, including noise contamination, signal complexity, interpatient variability, and the need for real-time analysis, hinder the accurate and efficient extraction of clinically relevant insights. This paper proposes a novel multi-strategy machine learning approach for enhanced psychological signal processing, specifically focusing on ECG analysis within intensive healthcare settings. Well, our introduction is that the ECGs are a cornerstone of modern cardiology, providing a non-invasive window to the electrical activity of the heart. Accurate and timely analysis of ECG signals is essential for diagnosing wide range of cardiovascular diseases, from arrhythmias and ischemia to heart failure and congenital defects. Well, furthermore, the increasing volume of ECG data generated in modern healthcare settings necessitates automated and efficient analysis methods. And our problem statement is that application domain specific problem is that the cardiovascular diseases are a leading cause of death globally, making timely and accurate diagnosis crucial, especially in critical care settings. And the traditional ECG analysis methods, including visual inspection and some machine learning techniques, often struggle to effectively capture the subtle but critical patterns within ECG signals. And our proposed solution is that this project addresses the challenges of ECG analysis by integrating deep learning, feature extraction, and knowledge distillation within a teacher-student model architecture. And this teacher model, leveraging its high capacity, learns to discern variations in ECG waveforms despite interpatient variability and data heterogeneity. Our dataset description. The cornerstone of our experimental evaluation is the widely recognized MITBIH arrhythmia database, a benchmark dataset in the field of ECG research. This publicly available resource, maintained by PhysioNet, provides a valuable collection of annotated ECG recordings, offering both the raw physiological signal data and expert-derived labels for a variety of arrhythmia classifications. The visualizations of the EDA. Well, first of all, we have in this section, we present 21 visualizations that provide insights into the performance and interpretability of our proposed framework, and each figure includes a title and explanation. Well, for the first part, the ECG signal for one patient will be visualized, and the visualization steps and operations subject to DSP Caution, the EKG signal load, the ECG data from a CSV file. And the next part is the MLII and V5 from patient ID 100 over 30-minute period. Well, by comparing two plots, you can observe differences in waveform amplitude and morphology due to the different lead placements. If there are abnormalities, they might appear as irregularities in the waveforms. And the next part, where this figure displays descriptive statistics for the MLII and V5 ECG leads, providing an overview of their distribution. Well, we can interpret this figure. Well, if the mean is close to 0, it suggests that the signal is well balanced around the baseline. And a high standard deviation might indicate large variations in the signal, which could be due to abnormal heart activity, noise, or strong ECG deflections. For the next part, the next figure consists of a 2x2 grid of subplots visualizing both the time domain and frequency domain representations of the MLII and V5 ECG signals for the first 8 seconds. And the first key observations is that the time domain plots allow visual inspection of normal and abnormal heart rhythms. The frequency domain plots help identify dominant frequencies, noise, or artifacts in the ECG signals. And if noise or power line interference is present, it may show as peaks in the frequency domain plots. The next part is the frequency response plot of a fourth order Butterworth bandpass filter. And the key observations, it preserves important ECG components. The 0.5 to 40 Hz range captures most ECG features while removing noise. Useful for ECG pre-processing. This filter is commonly used in ECG signal processing to clean raw data before further analysis, such as heart rate detection and feature extraction. Well, the next part is the two plots, each comparing the original and filtered ECG for the MLII and the V5 leads. Well, the filtered signals should appear smoother and more defined than the original ones. The bandpass filter improves signal quality, making it more suitable for further analysis such as heart rate detection or disease analysis. Well, my colleague can take from there.
My name is Teacher Z. Elvis, and I'm taking you through our EDA and probe and concept paper. Here you shall see a frequency spectrum plot of our visualization ECG obtained using the first frontier. And here we observe that the dominant frequencies in the 0.5 to 40 Hz range indicate that the ECG signal contains essential heart activity. Basically, the unwanted high frequency components, such as those above 50, may need to be removed using low pass band pass filter. And if the plot shows low frequency component that is less than 0.5, it may indicate baseline drift, which should be corrected using high passing fitting. This visualization shows a comparison plot of raw versus filtered ECG signal. And here we observe that the bandpass filter 0.5 to 45 Hz effectively removes the low frequency baseline wonder that is less than 0.5 and high frequency greater than 45 Hz while preserving ECG features. And a filtered signal is normalized, ensuring values remain in a 0 to 1 range, which is helpful for machine learning models, as you see. Basically, the visualization here shows the RR interval plot, and here the irregular RR intervals and high HRV could indicate arrhythmias, stress, or other cardiac abnormalities, as you see in the visualization, and extreme HRV values may require further medical analysis. For example, atrial fibrillation and bradycardia or tachycardia. Basically, here we shall see a Poincare plot, a graph method for visualizing heart rate variability. And here we observe that small scatter that are concentrated near the origin, they suggest low HRV and a stable heart rate, which possibly indicates this stress or controlled heart rhythm. And here, the large scatter spreaded further away from the origin will indicate basically high HRV, which shows greater variability in the RR interval, which is generally a sign of good cardiovascular health. And the broad circular plot can be associated with healthy autonomic function, while more linear plots suggest potential cardiac regularities. Another visualization shows a frequency spectrum plot of the filtered ECG signal that is obtained through the FFT, the first frontier transition. And the key observation here, we see the fundamental frequency at around 0.8 to 1.5 Hz. That indicates the heart rate. And the plot shows how the signal is distributed across defined frequencies that reveals the heart rate rhythm and any noise in the signal. And the low frequency rate from 0 to 1 is typically where the primary ECG lies. And here we see a correlation matrix object that uses the DF-core method. And here the correlation matrix object is then visualized as a heat map where each correlation value is color-coded and usually with cooler colors for the negative values and warmer colors for positive values. And this visualization here will show the power spectral density PSD of the ECG signal across different frequencies, as you saw on the plot. And the x-axis represents the frequency in hertz, ranging from 0 hertz to the nearest frequency, that is 180 hertz for sampling rate of 360 hertz. And the y-axis basically represents the power at each frequency, shown in the algorithmic scale. And this allows us to observe the relative strength of the signal at different frequencies, especially when the power values can span a wide range. And the type of analysis is useful in understanding the frequency of the content of the ECG signal and can help in filtering out noise, among others. And here we see a 2D heat map that represents continuous wavelet transform. And we observe that time frequency representation, the CWT, provides a time frequency analysis showing how the frequency content of the ECG signal evolves over time, and this is useful for detecting transient features or variation in the signal that occur at different times. Here we see a histogram that represents the distribution of the ECG signal's amplitude, and we observe that signal amplitude distribution, for example, the signal has a narrow distribution, and it means the amplitude values are clustered around a small range, and wider distribution suggests more variation in signal's amplitude. Here we see a box plot that shows amplitude variation of the ECG signal across two leads, that is MLII and V5, and we observe that amplitude distribution, the box plot provides visual summary of the distribution of the ECG amplitude for each lead, and you can quickly see the median amplitude and the spread, which gives insight into how much variation there is in an amplitude. And the comparison leads, you can compare the amplitude variation between the MLII and the V5 leads. We see a DFA dependent fluctuation analysis, a plot, and here the DFA plot, a log plot, shows the fluctuation of RR interval across different scales, and the scaling behavior will help in understanding the long-range correlations in the RR interval time series. And the missing value checks, the output will list the missing values for each patient's data that shows how many missing values exist in each column. And with this visualization, we observe that this is the V5 signal of the ECG data over time, and we observe that the plot will show how the V5 signal changes over time, capturing variations such as P wave, KRS complex, and T wave depending on the ECG data's characteristics. And the orange line will represent the signal's variation. And here we see the correlation between ML5 I and the V5. And here, the visual comparison, here we shall see that the side-by-side plots will allow you to visually compare the distribution of the two leads, and which helps in identifying whether the signal distribution are similar or if the lead has more varied amplitude. And here we see a visualization. It is a line plot showing the first 1,000 data points of the MLI signal from the ECG data. And we observe that the plot will provide a visual representation of the ECG signal for the first 1,000 samples, which likely corresponds to approximately the first few heartbeats of the patient. And here we see a smooth version of the ECG signal by the first 4 heartbeats, and we observe that the plot provides a smooth view of the ECG signal, which is useful for visualizing the overall trend and identifying the heart electrical activity without being distracted by high frequency noise. With that, that is all for our group and our topic. Thank you.